Hi everyone, this is Suruj, and in this video I'd like to talk about the Dream-in-4D, that given a text prompt it can generate 3D shapes that are moving. But before watching this video, make sure you already know how this STS loss is working, otherwise watch the Dream Fusion video. And yes, I hope you enjoy it, and let's just see how it works. Before talking about the method, I'd like to talk about one important challenge in text-to-4D generation that we have to consider. That is, once we create a 3D shape, in this case a dog with the shape, if we rely only on image and video diffusion models for 3D generation, we have a risk of multi-view inconsistencies that in this example you can see this dog has two heads because the image diffusion models simply have no idea about the 3D shape, and this artifact is called Janus Problem. And if we have this sort of artifacts in the static 3D object, then when we add motion, we see that the motion of the game doesn't seem natural. So one thing this paper tries to solve is this issue and then correctly generate the static object and the motion after that. And now let's just talk about Dream-in-4D method. Our initial input is a text, like a panda is riding a bicycle, and we want to create a 3D object with the movement as the output. What they do in this method is, initially they define a static stage, like all you see is a panda sitting on a bicycle without any movement, and they try their best to have a high quality output so that later in the next stage add motion on top of it. And one way to make this happen is relying on 2D diffusion guidance, that you can initialize a nerve model and train its weights using 2D diffusion guidance, that is STS loss. If you don't know about the nerve or STS loss, I have a YouTube video about that I already mentioned this in the intro, but you can just go and look at the Dream Fusion video and see how it works. But relying on this 2D diffusion guidance has the issue of Janus problem that I mentioned already in the challenge. So to mitigate this issue, they said let's use a 3D diffusion guidance instead of 2D. And by 3D I mean something like MV-Dream, that in addition to text, it receives the camera orientation as the input and has a 3D understanding. And for training the weights of the nerve, we again use the same STS loss with a tiny bit of reformulation that uses X0 instead of noise. And now that we have a 3D understanding, the result should be something that seems much better, but still there is an issue. You can see that on the prompts there are some details like a cat singing or a fox playing video game, but you don't see any microphone for the cat or any game controller beside the fox to play the video game. And the reason why is because the MV-Dream is trained on a synthetic dataset called Objaverse that has some noisy 3D data inside, and the MV-Dream work filtered out the ones with a low clip score and kept 350,000 objects, which is significantly less than Stable Diffusion that is trained on billions of data and has a better understanding of different layouts. So as a solution, they said let's use both of the 3D diffusion and 2D diffusion guidance and control their effect by changing the lambda hyperparameters, where they control STS losses of 2D and 3D and their effect on overall loss. And using this simple trick, you can see now that the generated results don't have the Janus problem and the layout contains a better quality and does not miss details provided in the prompt. And once the 3D object is formed, the next stage begins, which is the dynamic stage. In dynamic stage, we keep the trained weights of the nerve model from static stage frozen because we want to add motion using video diffusion guidance by applying STS loss, and since video diffusion models are typically trained with a lower quality data compared to image, they have the potential to degrade the quality of the static object. And for modeling the motion, another MLP for deformation field is trained that given a point in a space at given a time frame, it has to output the canonical position of that point in the static object that we have, and that way we can model the motion. But aside from the overall pipeline, there are a tiny bit of details that are very important for the final quality. The first thing to note is that the objects have limited elasticity and velocity, so the deformable field that we have to train is expected to be smooth, both spatially and temporally, and because of that they have used 4D multi-resolution hash-encoded feature grade, followed by this 2022 paper that proposes a method called Instant NGP, and inspired by that idea they use different resolution for static and dynamic. Specifically for static scene, the base resolution is 16 x 16 x 16 and the maximum resolution is 4096. And for dynamic scenes, because of limited elasticity and velocity, the base resolution is 4x4x4x4, and the maximum resolution is 232. And in case you don't know what I mean by base resolution and maximum resolution and how it is even possible to have a giant resolution and still make it doable to train, I will give you a little bit of background about how the multi-resolution hash encoding in the instant NGP paper proposed in the 2022 works. Let's say we have this input image and we want to use the implicit neural representation, or INR, to represent this image. In INR, we train an MLP that receives XY coordinates of where the pixels are located, and as the output, it gives us the RGB values. After training the INR with a single image, we can have a small neural net that encodes all the information within the image, because I can give it all the pixel value coordinates as input, and it gives me the RGB values, and put them together and have the image. So the weights of this neural net represents somehow the image, and since it is not interpretable, we call it implicit neural representation. And one challenge of INR is its scalability. Like if I have an image that has gigabytes of pixels, then it requires a lot of weights in the neural net, and it takes a lot of time to be trained. But what is cool about this multi-resolution hash encoding is that you can train this huge image within a few seconds, and then if you zoom in, you can see every single detail of it, even though the neural net that is trained on is super lightweight. Back to our example, to explain how this works, we can divide it into something like 2x2 greedy structure, and this 2x2 is the base resolution of our image. Then we define a hash table with the size of t as the hyperparameter denoting the number of entries, in this example 7, and f as the feature dimension in this example 2. And then let's assume that we want to find the values of a certain pixel like this one. To do that, we first look at the corners of the grid where the pixels falls into, then pass these corners to a hash function, and that gives us some values that are some indices of a hash table. We grab the corresponding values, then linearly interpolate the features to get the feature vectors y. But this is for the base resolution that is 2x2 in our case. And as an example, if you want to see another level in the hierarchy, on 3x3 resolution we have these blue grids that again we look at the corners, pass them to hash function, and have some value outputs. And again we have a hash table specific for this resolution with the same hash table size as the previous one, and we linearly interpolate them and concatenate the result with the previous one. And optionally, like for the nerf case that we have some auxiliary information like camera rotation, we concatenate them as the xi vector, which denotes by green. And once we do it up to a maximum resolution, we pass these high-level features instead of xy coordinate to the neural net to predict the RGB values in the case of image reconstruction, or radiance fields in the case of nerf. Hopefully this short explanation about it makes sense, and sorry for Jujutsu fans if we only have red and blue in this example and not the purple. Hopefully in the future videos we'll see. And they have shown in this figure that if we don't use the multi-resolution grid, then we cannot see local motion patterns like around the mouth or fin area, and it doesn't move. While if we use it, then we can observe local movements in those regions. And the other trick is this video diffusion guidance loss that is a bit different than the STS loss I explained in the Dream Fusion video. The loss they use is made of latent loss and decoded loss. In both loss functions, they use the canonical nerf the deformation field network to render a 24-frame video. Then they add noise and use the video diffusion guidance to denoise it, but instead of using a noise similar to STS loss as supervision, they use one-step diffusion and denoise it to reach the generated video in a single step. And in a latent loss, they use the latent of the generated result as supervision, and in decoder loss, they decode the latent and use the decoded video in RGB as supervision. And this new version of STS loss function is proposed in Haifa paper from ICLR 2024 that they say we use latent in addition to RGB values in loss, since RGB values alone result some color bias in generated results. And for the choice of video diffusion model in the loss function, they have tried model scope and zero scope, and both can generate promising results. But even if we do all the things I just explained in the video, you still see the results with lots of spatial and temporal jitters as the outputs. And there's one final trick to solve this jitter, and that is total variation or TV loss to ensure we have a spatial and temporal consistency. So the video diffusion guidance can be defined using the STS loss I just explained in addition to TV loss for regularization, with a large regularization scale as a strong constraint. And that is about text to 4D prompt. And the other cool application is by using an image instead of text for image to 4D generation. To do that, they have just modified their diffusion guidance to receive image instead of text. And for 3D diffusion, they use 0123 XL instead of NVDream. And for 2D diffusion models, they use Deep Fluid F instead of a Stable Diffusion. And by the simple trick, we can have an image as the input and generate a 4D and see things like a cartoon dragon that is running or a rabbit that is eating lettuce. And the final thing they tried is personalized 4D generation, that they replace the Stable Diffusion with Dream Booth so that you can give it a bunch of images and fine-tune the diffusion model to generate your personalized images. But the results doesn't seem identical of the given image much. And yes, that was all I wanted you to know about this paper. If you enjoyed it, don't forget to like and subscribe, and until the next video, goodbye.